Hi everyone, welcome to another video for the Reproducible Rehabilitation Research Education Program, or ReproRehab. This is part of our series in videos that is designed to give you a crash course introduction to the programming language R. In our previous video, we talked about installing R and RStudio and getting your basic libraries installed and then opening those libraries locally on your machine. In today's video, we're going to talk a little bit more about basic functions in R, how to create objects, and the properties that objects of different classes have. In subsequent videos, we're going to take a more project-focused approach, where we're really going to be learning specific things in order to import data, merge the data together, clean that data, and then visualize that data. So in this particular video, it's going to be a little bit more abstract to highlight some of the general functionality of R. But again, we're not going to cover everything. Our goal is to give you a foothold of R knowledge that you can then subsequently apply after the crash course when you're doing kind of guided learning with the teaching assistants that are part of the ReproRehab program. So first, let's talk about creating a basic object in R. The way that this will work is I will assign a value to my object, and I will also be giving it a name. So I'm going to create an object called X, and I'm going to assign to it a value of 2 using the equals sign. When I do that, I can run that line of code by highlighting that line with my cursor, pressing Control Enter if I'm on a PC, or Command Enter if I'm on a Mac, or I can always just highlight the line and then press Run up here. I don't even have to have it highlighted. I can have my cursor anywhere in that line, right, and then hit Run or hit Control Enter in order to execute that line of code. We can see then that in our script window, that line of code gets actually run down here in the console window, and the result of that, right, assuming that everything runs correctly, is going to kind of pop up somewhere else on our machine if it's designed to return something. If there's an error, that's going to show up down here in the console window, but in this case there is no error, and what happens is we see this value of X, which if we hover our mouse over it, it tells us it's a numeric, and it has a value of 2. So next, we can use that variable to kind of update the value of itself. So this is a fun thing about assignment, is it can take the same object and then assign it to a new value. And this is an important thing about how assignment works. So assignment, you know, if we just use the equal sign, we can read that, you know, in the same way we would normally read a mathematical formula to say that X is equal to the result of whatever we're doing over here. So it's going to use X as 2 plus 3 on the right-hand side of this first, and then assign that to a new value of X. However, if we wanted to be really explicit about the direction of that assignment, rather than the equal sign, we can also use the assignment operator in R, which looks like this. So it's an arrow pointing in the direction that I want that assignment to take place. And that's useful because it's more specific about the direction with which assignment is happening. And we could actually do assignment in the other direction as well. So you can use the equal sign. It's going to work probably just fine 99% of the time using the equal sign. But if you want to be a little bit more explicit about your assignment, you can use the assignment operator by combining a less than sign with a hyphen in order to create a little directional arrow. So now, keeping my cursor on that line of code, I'm going to press Control Return. You can see that X plus 3 gets assigned to the new value of X down here in the console, and the value of X has been updated in my environment to now be 5. So now, if I didn't want to actually change the value of X, but I just wanted to use it in some kind of calculation, I could say X times 3. X times 3 returns the value of 15, right? Because 3 times 5 is 15. And there you go. We're off to the races using R basically as a fancy calculator right now. But this is some basic R functionality. Next, let's create another object. We're going to call this object Y. And Y has the value of 2. And now when I have these two numeric objects, I can do things like divide X by Y. And X divided by Y returns in the console the value of 2.5. But now let's say I wanted to do something that was non-numeric. So I'm going to make Z the value word. And I'm going to put that in quotes. So Z now has the value over here in my environment of word. And if I hover my mouse over Z, you can see that this is a character. So a character is a type of object in R. It's a class of object, and characters, right, are just strings. They're just the letter form. You know, you could mix letters and numbers together, but they don't have a numeric value. They are basically discrete categorical types of data. And they're one type of data like this, the others being things like factors, which we'll get into in a little bit. But having having a character object is useful for now. So let's treat z as a string. And we'll try to multiply x by z, and you'll see that we get this error down here at the bottom, where we have a non-numeric argument to a binary operator. So this did not work, right, because z is non-numeric. So we can parse this error message pretty easily to help us understand exactly what went wrong in this calculation. This is a pretty simple one, right, because obviously we saw that z was non-numeric when we created it. But this is just to help you get a sense of, like, when something goes wrong, try to parse what that error message is telling you, and then think about, well, okay, what do I have to change? What do I have to go back and do differently in order to avoid that error message? So as you practice with R, you'll probably see a lot of error messages, and over time you'll get better at reading them and understanding what they're telling you. But if you ever get stuck, a great thing to do is also just Google that error message. Just pop it into your search engine and see if other people have had a similar problem to you in the past, and if they have found an answer that's similar enough to what you need to do to answer your current question. Let's move forward with some logical evaluations. So next we're going to look at x is less than 2, and we can hit command return in order to get execute that. And you see this evaluates to false because x is 5, and that is not less than 2. If I wanted to ask, is x greater than 2, that evaluates to true because, of course, x is 5, and that is greater than 2. But we have to be careful here because if we put in z is less than 2, that does not return an error message. That actually evaluates to a false statement. And if we do z greater than 2, similarly, that does not return an error message. That evaluates to a true statement. So why were we not able to do x times z, but we can ask if z is greater than 2? Well, z is a character, 2 is a numeric. So the 2 is going to get coerced into being a string by default in order to try and establish this equality. And then the strings are compared in their ASCII order. So that's, sort of your dots, your hyphens, your symbols come first, then your numerics, then the alphabet, right? So because 2 is going to come before the W in word, right? Z less than 2 is going to evaluate to false. But because the W comes after 2 in the ASCII order, Z greater than 2 is going to evaluate to true. And so if you had thought that this probably should return some kind of error message, this is an important lesson in going back and always checking your code to make sure it really is returning the values that you think it is, so you can understand precisely what your code is doing. And if we ever wanted to actually check on the class of these different objects, R has some handy functions like is.character. So I can ask, is Z a character, right? And that is true. That tells me that Z is a character. Is Z numeric? That tells me false, right? So we know that Z is not numeric. So these are pretty simple functions, but they are going to come in handy when it comes to doing some quality control checks and really understanding our data to make sure that the data are coded the way that we think that they are and that they'll behave the way we want when we put them into some more complicated functions later on. So next, let's look at some other data types that we have. The first one that we'll consider is vectors. So when we created this object x, we talked about it being an object that was of the class numeric, but x was actually, technically speaking, a vector of length 1. Right? It was a single observation, but we could have a numeric vector of lots of different lengths. So I could also make x the concatenation of the values 2, 3, and 4. The other way you can think about this C is almost like x is a column, because for instance now if I print x to the screen, you can see I've got 2, 3, and 4. So that's an array, right? It is a vector that is 3 observations long and 1 observation wide. And I can encode that and use that as a numeric object the same way I did when x was just one number. So keep in mind, x is now the values 2, 3, and 4. Y is the value of 2. What do you think is going to happen when I multiply x by y? Well, when I multiply x by y, the smallest vector is actually going to get repeated until it equals out to the units of the larger vector. So as long as my vectors are divisible, this kind of multiplication is going to work, and the smaller vector is just going to repeat when I do that multiplication. And my result is 4, 6, and 8. Let's change this now, though, so that y is also a vector of length 3. So now x is the values 2, 3, and 4. Y is the values 0, 1, and 2. what do you think is going to happen now if I multiply x by y? Well, when I have vectors of equal length, what we're going to end up with is a vector-wise operation where the first item in each vector is getting multiplied together, and the second item, and then the third item. So the resulting product vector of x times y gives 0, 3, and 0, because 2 times 0 is 0, 3 times 1 is 3, and 4 times 0 is 0. Now, let's create a character vector. So we'll create z, which has the values red, red, blue, blue, and green, green. Another function that's very handy is the summary function. So if I ask for a summary of this character vector, it tells me that it has a length of 6, because there are 6 observations within this vector. And it has the class of character and the mode of character. Another thing I can do is look at the structure of z using the str command. And that's going to tell me something really similar. It is a character with 6 observations, right? It tells me it goes from 1 to 6. And then because this is relatively small, it prints all of them to the screen. If my vector was a lot bigger, it would probably cut it off so you wouldn't see all of them at once. But now let's coerce z into a factor, which is another type of string. But what a factor is a separate kind of index. It tells me what the labels are, and then it keeps track of how many observations there are that meet each of those labels. So now when I ask for a summary of z, after converting it into a factor, I see that I have 2 blue observations, 2 green observations, and 2 red observations, which is different, right, than when it was a character. So in the character case, it doesn't keep track of the fact that red and red are the same string. It just knows that red is a string, red is a string, blue is a string. When I have coerced z into being a factor, now it recognizes that red and red are the same, blue and blue are the same, and green are the same, and it keeps track of each of those pieces of information. I can further see that if I ask for the structure of the z variable using str, where it shows that it's a factor with 3 levels, being red, blue, and green. The next type of data we might want to create is a matrix. So let's go ahead and create a vector, which we'll call mat data, short for matrix data, and it's the numbers 1 through 9. So you can see that when I run that code down here in my console, mat data shows up in the environment, and it has observations 1 through 9. I can also print mat data directly to the screen if I didn't want to look at it up here in my environment. But again, nothing too special here. We're just creating nine numbers that we can use to create a matrix. Given those data, now I can use the matrix function to pull them into a matrix. So I can create something called matrix 1, and which is going to be assigned the result of the matrix function. And the matrix function takes 3 arguments. I need to tell it what data are going into the matrix. I need to tell it how many rows there are in the matrix. And I need to tell it how many columns there are in the matrix. So by specifying mat data, which is a vector with 9 elements, and n row equals 3 and n col equals 3, what I end up with is a 3 by 3 matrix where I first get 1, 2, 3 in the first column, 4, 5, 6 in the second column, and 7, 8, 9 in the third column. So that has bent my 9-item vector into a 3 by 3 matrix. If I wanted to interact with individual items in that matrix, I can use the square brackets to subset any type of, or many types of data in R. So I'll say mat1 and then square brackets 1 comma. And what that will return is the first row, because we're using row by column notation here. So when I say 1 comma nothing, what I'm asking for is the first row, but all columns of mat1. Next, when I say mat1 square brackets nothing comma 3, I'm asking for all rows, right? But the third column, because again, it's row by column notation. So when I don't put anything before the comma, what I'm getting is all of the row values. So this, if I wanted to actually isolate to a particular observation, I could give it both a row and a column value. And now I can get the first row and the third column, which is, of course, a 7. So that allows me to kind of navigate my way around a matrix in order to access individual items that I might want. Something that is like a matrix, but very different, is a list. So matrices have to have a certain number of dimensions, right? They can be square or rectangular, but matrices are always going to be combinations of numbers, and every column in the matrix is going to have the same number of rows as every other column, and every row in the matrix is going to have the same number of columns as every other row in order for everything in that matrix to be filled in. A list, alternatively, is kind of like a collage of different data types. So I can put characters in a list, and I can put numerics in a list. I can have the list really be made up of anything that I want. So this gives some lists some strengths and weaknesses, because it's great to have that kind of flexibility. However, one of the disadvantages of the list is that it can be a little harder to navigate around, because, for instance, after I create this list, which we've called my list, let me print it to the screen. Now you can see I have an element to the list, which is A, an element to the list, which is B, and an element to the list, which is C. And now A only has one observation, B only has one observation, but C has 1, 2, 3, 4, 5 observations inside of that element. So that makes it a little bit trickier to potentially move around in here, but the same basic principles apply. And one thing you'll note is that when I print my list to the screen, you see I get this $A, and that $sign is how you delineate different elements inside of a list or inside of a data frame, which is something we'll talk about in a second, using R. So if I wanted to see just the things within element A of the list, I can say my list $A. If I wanted to see just element C, I could say my list $C. And now, because C is a vector, I can move through it using the same subset brackets that we used before. So if I wanted the third element, the third observation from element C, I could say my list $C, and then in square brackets, the number 3, and that's going to return the third observation from C, which is 89. Now, related to list, there is something called a data frame in R. And in order to create a data frame, we're first going to create two different variables. I'm going to create a variable called sex and a variable called height. And those variables, you can see, have 20 observations. So sex is a factor with 2 levels. Male gets repeated 10 times, and then female gets repeated 10 times. And height is a vector of 20 observations, where I'm generating some randomly distributed normal data, and I'm going to get 10 observations that have a mean of 67 and a standard deviation of 2.5. So that corresponds to a distribution of male heights. Then I'm also going to randomly generate from a normal distribution 10 observations that have a mean of 64 and a standard deviation of 2.2, and that's going to correspond to my 10 female heights. Once I have those two vectors, I can use the data.frame argument to stitch them together into a data frame, and I'm going to call that data frame dat1, and I can print dat1 to the screen, and it will all be printed down here in the console window. So you can see, all right, there's my sex vector, which is now actually a column. So it's my 10 male observations and then my 10 female observations. And then I have a height vector, which again used to be a column standing on its own, or it used to be a vector standing on its own, but now is a column inside of that data frame. So I have my randomly simulated male heights and my randomly simulated female heights. One thing to note here, don't worry if your height numbers look different. We used the rnorm function up above, and that's going to randomly generate values from a normal distribution that have this particular mean and standard deviation. Now, there are things we'll show you in the future to help you control simulations so you get exactly the same result. But because I did this random normal distribution here, and if you're running this code, you'll get a different random normal distribution on your end, so your heights will be different values, even though they should have pretty much the same mean and standard deviation. So now that we have this data frame, it's getting a little bit bigger than some of the vectors we've looked at previously. So a nice easy way to visualize some of that information is to use the plot function to look at height as a function of sex, and then the data that we'll pull from our data frame dat1. So when I have these two different things in a data frame, one is a numeric variable, the other is a factor variable, the plot function can intelligently make a nice little plot for me. And again, your plot's going to look a little bit different, but you should probably find that the females have a lower median height and that males have a higher median height. Given my two random samples that I generated just now, these actually look pretty similar and they're not all that different, which is fair because the means are only 3 inches different in reality. But you can see there's quite a bit of overlap in both of those distributions. Yours might look a little bit different because, again, they were randomly simulated. Okay, so next, let's think a little bit more about functions and arguments and how we can use them in R. But there's all kinds of functions out there, and you can even start learning to write your own functions near the end of ReproRehab. But for what we're doing right now, we're just going to talk about some really basic functions. So let's start with our numeric vector x. If we want to get a summary of x, we can use the summary function, and the summary function takes one argument. We just have to pass it an object, and it will return a summary of that object. If we ever have a question about a function, we can just put a question mark before the function name, and then we can have, question mark summary and run that in order to get the help window to show us a description of the summary function. And we can see here it says summary is a generic function used to produce result summaries of the results of various model fitting functions. The function invokes particular methods, which depends on the class of the first argument. So class and methods and all these things are underlined because they will take you to additional pages in the help menu. But let's think about this a little bit, what this last part means. It depends on the class of the first argument. And class is something that we've talked about before. So let's look at, class X is a numeric variable. And we saw that when we took a summary of X, it returned the value. It gave us the minimum, the first quartile, the median, the mean, the third quartile, and the maximum. So it's calculating some descriptive statistics for us when we pass it this numeric variable. If instead we were to pass the summary function something like dat1 $sex, which is the column for the sex variable in our data frame, it's going to give us a different set of descriptive statistics. In this case, it gives us the frequencies for males and females in that fake data frame we just created. So again, this is what why the class of the variable matters and is going to change the output you get from the summary function. And for instance, if we were to check the class of that sex variable, it is of the class factor. So the results of the summary function will change depending on if I'm giving it a factor, a character, or a numeric vector. And so it can be a really useful tool, but we have to make sure we're passing the right information into it in order to make sure we're getting the information that we want out of it. Let's quickly take a look at some of the other objects we've created to see what kind of classes they are. And again, class is a function, and it takes one argument. So I can just tell class, what is the class of Z? Z is a factor. What is the class of my list? Well, it's a list. What is the class of dat1? It's a data frame. So that's probably, we wouldn't need to check this because we just created all these things, so you might remember what they are. But especially if you're importing data or working with something you're not familiar with, the class function can be a really helpful way of making sure that the variable you're looking at is coded the way that you think it is. Similarly, we can use the structure function to give us a bit more information. So class of my list just told me it's a list. Structure of my list actually returns several pieces of information. So it tells me it's a list of 3 elements, and then it gives a description of what each of those elements are. So A was numeric, and it has one value, 2.5. B is logical, and it has one value, which is true. C is an integer, and it has 5 values, 91 down to 87. So the structure function, the class function, and the summary function are all really useful ways for helping you understand your data better, and especially doing quality assurance checks to make sure your data really mean what you think they mean. Beyond those, we can use some really helpful functions that we'll get into in subsequent scripts to do calculations. A really basic one would just be the mean function. Now remember, x is the numbers 2, 3, and 4. So if I take the mean of x, it's going to return a value of 3. But on line 97, I'm actually going to update x to take on to be a longer vector. So I'm going to use the append function, and I'm going to say take the current x and then append to it the values NA, 0, and 15. So append is a function that takes 2 arguments. I need to tell it what vector I'm starting with, and then I need to tell it what vector to append to the end of that starting vector. If I do that, now when I print x to the screen, you can see that x is my original vector, 2, 3, and 4, plus the values of NA, 0, and 15. So now let's take the mean of this slightly longer vector. Well, when I do that, the mean of x returns NA. It's no longer 3, of course, because we added some additional numbers, but now it's returning this missing value or not applicable symbol. So why is it doing that? Well, because I have a missing value in the vector now. X contains an NA, and R doesn't know what to do to calculate the mean of a set of numbers when one of them is missing. Now, we only said mean of x up here, but the mean actually can take multiple arguments, and one of those arguments is na.rm. So I can say, now take the mean of x, and na.rm is short for na_remove. So na_remove I will set equal to true, in which case it will remove all of the NAs from my vector first, and then calculate the mean of x, which, when that NA is removed, happens to be about 4.8. Now, I mentioned that the mean can take more than one argument, but up here, obviously, we only showed it taking one argument. So how do I know how many possible arguments something can take? Well, I can write $mean, then I can hit return, and it will take me to the help page for the arithmetic mean. And you can see that it has the arguments x, trim, and na.rm, and it can have further arguments passed to or from other methods. So this is something important when you're looking at R code in the future. Not all of the arguments have to be written every time. There are going to be certain defaults that are included when you run that function. So you can see that by default, the mean function sets trim to 0, so no values get trimmed. And it sets na.rm equals to false because it assumes you don't want to exclude missing values. For instance, maybe you want to know if a missing value gets in there, and then you want to stop the calculation and go back and look at it. So just because we have these arguments doesn't mean we have to write them every time, but you have to be careful then when you're looking at arguments in the future, because when you're looking at functions in the future, because there might be some arguments that someone is not writing because they're accepting the defaults, but that doesn't mean you don't have control over them. So it's always good to use the question mark, go to the help menu, and look at the function you're using to really make sure, hey, am I specifying everything that I can specify? And most importantly, are the defaults set to the things that I want? Okay, so outside of functions, one really useful thing that we can do from our script is to install and load new packages. So an important package that we're going to use moving forward is the tidyverse package. And the tidyverse package is a pretty big one because it actually is a suite of packages. And when you install tidyverse, you're actually installing multiple things. So as you can see that we're running through this and a whole bunch of things are happening because when I'm installing tidyverse, it actually, like I said, is installing a bunch of different packages that make up the tidyverse. So I got a lot of useful tools for plotting like ggplot. It also includes tools for data wrangling like dplyr. It includes tools for working with dates like lubridate. But all of those packages now you can see kind of have gotten installed when I installed the tidyverse package. However, and this is a good example of why this comes in installation and loading the package comes in two different steps. The package is now installed on my device, but to actually load it into the current R session, I want to use library. And then that will actually open the package into the current session. And what I can see is here's all the packages that have been attached, but I actually have some conflicts. So this is why we don't necessarily always want to load everything that we've installed, and you actually have to install and load as two different steps. So there's a function called filter in dplyr, which is currently masking a function called filter from the basic stats package. And if I didn't want that, right, it would be really inconvenient if dplyr loaded every time I opened R. Similarly, there's a function called lag, which is currently masking a function called lag from the basic stats package. And again, that's only going to happen if I load dplyr, in this case by loading the tidyverse. But if I didn't want that, right, then it would be helpful to have the option of loading tidyverse. So because I might only want specific functions in certain situations, and I don't necessarily want to load everything I've ever installed at the beginning of one session, R gives you control over exactly what what packages you're going to use by separating installation and the loading of a package into two separate steps. Next, we can set our working directory. So we have a few really helpful features for doing this. So the first one is getWD, which allows you to get the working directory. And you can see that that's currently set to my documents folder. And another one is list.files. And what list.files allows you to do is see a list of all of the files that are currently included in your working directory. So there's quite a few things in my documents folder. I probably need to delete some of them. But this allows us to look for things that we might think are important and really copy a file name that maybe we want to use. So what we can do with this though now is start to look in different places in order to really set the working directory that we want. So one of the things inside of my current working directory is a GitHub folder. So if I wanted to look inside of that GitHub folder, I could say dot, which will take the current working directory and then append to it the file name GitHub. And so then I can look inside of the GitHub folder. So then you can see, aha, okay, list files.github returns this list of folders. Inside of my GitHub is something called ReproRehab. So I could say list.files ReproRehab. And you can see there's files, there's a data folder, there's a README file, and then there are several scripts inside of this scripts folder. So I could set this as my working directory by now using the set working directory function, or setwd. So if I said set working directory is /github/ReproRehab. Now if I say get working directory over here, you can see it returns the now updated path to my working directory being the ReproRehab folder. You can also do this manually. If you wanted to go up to like session, you can say set working directory, choose directory. And in this case, it's going to default to ReproRehab because that's where we just were. But you could navigate there again by going to the documents, going to GitHub, going to ReproRehab. And then this is where we want to set our working directory because it's going to give us easy access to both our data folder and our script folder. And again, if you're familiar with MATLAB, you're probably used to the idea of a working directory, but a working directory is telling your computer where to look for certain files. So if you don't want to always give your computer a big long file path every time you're about to read a file, it's really helpful to create a project folder and put the things you're going to need within subfolders of that folder. Because then you can set your working directory to the project folder and then, occasionally go into the data folder when you have to import data. And if you're going to save a figure, you can save it in the figures subfolder, right? If you're going to save an output from a statistical analysis, you could save it in the output subfolder. But by keeping your working directory at the level of the project folder, that kind of makes it easy to dip in and out of your different project folders. So to give you an example of that on line 118, we have our working directory set to ReproRehab. And again, if we look at that, we can see that there is something called data, there's readme.md, and then there's scripts. Data is a subfolder, so let's actually do list files within the data subfolder. And now you can see there's something called process data eeg.csv, so that's a CSV file. There's EEG subfiles. That has no suffix, so again, that's a folder. And then there's something called master, and then a bunch of stuff, .csv. And these are all data files we're going to work with in some subsequent videos. But we actually want to look, we're just going to look inside of the data subfolder, and we want to import this processed data. So we can do that using the read.csv function. And the read.csv function takes several different arguments. But the first one is I need to tell it where is the CSV located that I want to read. And read is basically a term like import, right? Or open. Read is like open, write is like save. So if I'm reading it from the disk, I'm reading it from my hard drive into the current R session. So I want to look in the data subfolder and I want to read the CSV file called data_processed_EEG. This particular spreadsheet has headers, so I'm going to say header equals true. And I want it to treat my strings as factors off the bat rather than just treating them as characters. So I can run that, it's going to create an object called data2 or dat2. And you can see I don't get any error messages down here in my console window. And if I look at dat2 up here in my environment, it's 2,640 observations with 13 variables. So if I wanted to look at that whole thing, I can click on this in the environment, and it's actually going to open up a tabular representation of the data like you might get in Excel. But this is, all 2,600 rows long by about 13 columns wide. So that's a lot to look at. So let me close out of that. And instead, what I might try to do is use just the head function to look at the first 6 rows of the data. So that's going to show me all of the columns, but it's only going to show me the first 6 rows, which is a slightly easier summary in order to see what's going on with my data. Again, this is a good situation where the number of arguments and the number of defaults isn't always clear. Head defaults to printing 6 rows, but I can give it a second argument explicitly. For instance, I can say head dat2, 10 in order to print the first 10 rows rather than the first 6 rows in order to check those data on my screen. So another situation that we're going to encounter is if you're not importing data from your computer, you might want to import data from the web. And to do that, you can still use the read.csv function, but rather than a file path on your computer, we're going to pass it a file path from the internet. So in this case, we're going to be looking at some simulated therapy data from my GitHub repository. So this URL is already going to be in the script. I'm not going to read the whole thing, but this URL, if you actually pasted this into your web browser, is going to take you to a CSV file that is stored online. So we can use read.csv in the same way. We're just going to give it a web address rather than a local address. We're going to say header equals true, strings as factors equals true. And then this data set is pretty small because this is just kind of a toy example we use in a stats class. It only has 18 observations of 3 variables, so I can print all of that data to the screen. And you can actually see dat3 then is a data frame that has 3 variables, whether people were assigned to a certain drug, whether people were assigned to psychotherapy or not, and then their scores on a fictitious mood questionnaire. So this is the kind of data you might get from a small randomized controlled trial that we have as the data frame in dat3.